So we are looking at section 6.2. We're looking at problem 71. That's about Newton's law of cooling. So both 71 and 72 are homework problems. I'm going to work through 71 so you get another example of Newton's law of cooling, and we're going to connect it back to what we did last year in pre-calc. And then your homework is going to be to take a picture of this problem. So I know that 6.2 is an assignment for you, but I really want to carefully check over this problem also. And so when you work this one out, you're going to submit that as a Canvas assignment. So I have something to grade. So let's see what's going on. When an object is removed from a furnace and placed in an environment with a constant temperature of 80 degrees Fahrenheit, its core temp is 1500 degrees Fahrenheit. 1 hour after it's removed, the core temp is 1120 degrees Fahrenheit. Find the core temp 5 hours after the object is removed from the furnace. So that was our first read. And then I would want to think about what's really going on here. So I'm taking something out of a furnace. I'm not focusing on numbers right now, just what's going on. So I'm thinking like maybe we're taking something that you made in pottery, some ceramics or something, and we're taking that out of a furnace and we're putting it into a pretty warm room here. But eventually the object is going to cool off, right? The temperature of the object is a lot hotter than the outside room, and so it's going to cause it to cool off. So that's the situation we have here. So it looks like when we have, so now I want to go through and I want to pay attention to numbers. So the room is 80 degrees Fahrenheit. It looks like it starts out at 1500 degrees Fahrenheit and it's going to cool off. So we know that. And then 1 hour later, we're down to 1120. We want to know 5 hours later what the temperature is going to be. So we know it's going to have to be a number less than this. It's going to be a lot less than that after 5 hours, right? So we just have some number sense about this. We're thinking about what's going on with the problem. So now I want to take a couple notes. We have a surrounding constant temp of 80 degrees. Surrounding constant temp of 80 degrees, which is pretty warm. And the object starts. So starts means t equals 0, time equals 0. Our temperature is 1500 degrees Fahrenheit. And then after 1 hour, we are at 1120 degrees Fahrenheit. And then we want to know the core temp after 5 hours. So Newton's law of cooling in a calculus course is not just a formula we're memorizing. It's thinking about proportions. And so Newton's law of cooling is actually that our change in temperature, so this is going to be y prime is going to be dy dt. So our change in temperature with respect to time is proportional. So is proportional means equals, and then proportional means I have some kind of constant of proportionality there. With respect to the difference between our object temp and the surrounding temperature. So our object temperature would be y in this case. Remember, dy dt is change in our temperature with respect to time. So our temperature minus our surrounding temp, that's 80. So this is what we're working with. So I want to go ahead and separate my variables out. And you could leave it as y prime, but I know we really prefer this notation. So first I'm going to multiply both sides by dt. And then I'm going to divide by y minus 80. And then I'm going to integrate both sides. So on the left, I have a natural log. This is the top is the derivative of the bottom. So if I took this was my u, y minus 80, my du would just be a 1 dy, and that's what I have on top. So I'm going to get natural log of y minus 80. Normally I would do absolute value signs, but if we think about it, this isn't going to be negative. The temperature y of my object cannot be less than 80. Y is going to have to be between 80 and 1500 because this is where it starts out and it can't cool off colder than the surrounding temp, colder than the room. So we just can get away with parentheses there. On the other side, when I integrate k with respect to t, I'm going to have kt plus some kind of constant. And then we know in order to make this a nice formula, something we can actually work with, I'm going to want to get y by itself. I'm going to want to exponentiate both sides. So the cool part is we could actually work with it in this form and do everything just with logarithms. So there is a different way to do this math problem. There's 3 different ways that I know of to do this math problem. But I want to take you through the one that the book is using, the one that's going to get you that pre-calc formula. So if I am raising something e to a power and I've got that natural log, I know here I just have y minus 80. And then on the other side, we know that if we have this great big exponent for e, it's really e to the kt power times e to that c1 power. So I know when I have the same base, I could add my exponents. So I could go from here to here by using that property, just like I can break it apart that way. So now I'm going to call this my constant c. So I'm just going to write y minus 80 equals c e to the kt power. And then I want to add 80 on both sides. All right, now I have to plug in some information because I've got 2 different constants here. I've got this constant that's going to give me that that proportionality constant to begin with, that is how we're cooling off, and then this constant right here also. So let's see. I know that at T equals 0, my temperature is 1,500 degrees. So I'm going to plug in some numbers. And it'll be k times 0. I know that e to the 0 power is 1. So this is just going to be 1,500 equals 80 plus c. C times 1 would just be c, and then I would subtract 80 on both sides, and then I get c right away. So right now I have, and I don't really have to write this down, but right now I have 80 plus 1420 e to the kt power. So now I'm going to have to go ahead and find k. So to do that, I know that after 1 hour, so that's going to be T equals 1. My temperature is, let's see, 1120 degrees Fahrenheit. So let's go ahead and plug that in. So y is going to equal 80 plus, oh, I don't want to write a y, do I? I want to put in my temperature. So 1120, 80 plus 1420 e to the k times 1 power. So let's subtract 80 on both sides. So that's going to be 1040 equals 1420 e to the k power. I don't really need k times 1, do I? And then I want to divide on both sides. And then I'm going to have to log both sides. So take a natural log. And that's going to give me k. And it should be like negative, ooh, I'm off the page, negative 0. Let's see, 311,436,158. And I know however many decimal places I carry through this problem is going to make a big difference. So now that I have k, I can actually write a formula here. So I have, and this is for this situation where we start out at 1,500 degrees and the surrounding room has a temperature of 80. We're going to get y equals 80 plus 1420 e to the negative 0.311 t power. So now that I have a formula to use, I want to know temp after 5 hours. And I think there's some creative spelling here. So I'm going to let my t equal 5. So y equals 80 plus 1420 e to the negative 0.311 times 5 power. So if I work this out, I think you get, I'm trying to read my writing on my paper, 379.889. So it's basically 0.9 degrees. But if you are to carry more decimal places, so if I use like maybe this whole thing, I'm going to actually get 379.2 degrees. And that's what the book has in the back. So you might be off by a little bit depending on how you round. So if you wanted your answer to be, a certain number of decimal places accurate, you would have to carry more places. And it's not hard to do that with our calculators. So just keep in mind when you check in the back of the book, you might be off by a little bit. So I wanted to link this back to the pre-calc stuff. So what I'm going to do is right next to this line of work, I'm going to write the pre-calc formula. The pre-calc formula was that the temperature as a function of time, so big T is temperature, little t is time, is going to be T sub S, so that's my surrounding temperature, plus T sub 0 minus T sub S, so that is going to be initial, so T naught is your initial temp, minus this one, this is your surrounding temp, times E to the negative KT power. So what that means is I could have gotten the 80 and the 1420 right away without using all that calculus stuff. And if you notice, I guess I don't really need this negative here because we get the negative later on anyway. So if I put my surrounding temp in here and then I put my T naught minus my surrounding temp in here, I would be like loads ahead on this. And you'll notice when we do, I don't want to put degrees, I just want to write 80. I really did not leave myself enough space here. So let's fix this. So I have 80 plus, when I subtract those two, 1420 e to the KT power. It gives me all of that stuff right away. So I wouldn't have had to do all my calculus work. I know that Mr. Veeder on his solutions is kind of just going to this right away. So I think there's some strength in remembering the pre-calc stuff. I also think it's really important that we know how to integrate and do all of this work. So there's two different ways you could work this out. One significantly easier if you memorize a formula from pre-calc. The other one is just remembering this idea of proportionality between our change in temperature with respect to time and the temperature, the difference between that and how much the surrounding temp is. So different ways to work the same problem, but we should get 379.2. I honestly, as Mr. Veeder has worked out stuff using this formula, I don't know that I care which way on a test or a quiz, but for this homework, I would really like to see you go through and crank through the calculus stuff. It's just on one problem that I want you to do that. So number 72, see if you can give me the calculus stuff.